Welcome to the lesson on state variables and their measurement. My name is Dale Fredlund and I am Professor Emeritus at the University of Saskatchewan, Saskatoon, Canada. This lesson is of a basic nature, intended to introduce unsaturated soil mechanics at the undergraduate and graduate engineering levels at universities. It is hoped that the notes will also be of assistance to practicing geotechnical engineers. The world of soil mechanics can be viewed pictorially as an ellipse, with a phreatic line designating the water table. The stress state variable used to describe saturated soil behavior is known as the effective stress. It is commonly abbreviated as the difference between total stress and pore water pressure. Above the water table, the effect of changing total stress can differ from the effect of changing pore water pressure. Consequently, the stress state needs to be viewed as taking the form of two independent stress state variables when it comes to unsaturated soils. So where do we start to develop a science based on the state variables that have been mentioned? Once appropriate state variables are defined, we can proceed to the determination of suitable constitutive relationships. The term constitutive relationships is used for any equation that is written to link state variables through the incorporation of an appropriate soil property and/or appropriate soil property functions. Equations for the three main application areas in soil mechanics are shown on this slide. These are the constitutive relations for seepage, shear strength, and volume change. Each of these physical behavioral areas will be developed during the next lessons. However, this lecture will focus on fully understanding the state variables for an unsaturated soil. I would like to start by providing a brief theoretical basis for state variables. You might not find this part of the lecture very exciting, but I think it is a little bit like medicine. You may not find it pleasing to the taste, but I suggest that it is important for your well-being as a geotechnical engineer. I trust that by the time this lesson is done, you might be able to answer the question, why are state variables so important? Terzaghi is given credit for coining and defining the term effective stress. It was this term that is credited for changing soil mechanics from an empirical art to an applied science. It allowed for the comparison of saturated soil behavior experiences from all over the world. Worldwide comparisons could be made because saturated soil behavior could be related to a non-material variable, that is, a state variable. Fung, a well-known author in continuum mechanics, assembled a science for a wide range of material behaviors, starting with a single phase material to multi-phase material. State variables form the basic building blocks for the development of a science. It is true for a single phase material, and it is true for a multi-phase material such as unsaturated soils. A logical question to ask is there a theoretical basis for state variables? And the answer appears to be found in the application of the two most important conservation laws of physics, namely the conservation of mass and the conservation of energy. Consideration of the conservation of mass leads us to the selection of deformation state variables. The deformation state variables allow for the mapping of the movement of either single or multi-phase systems. Consideration of the conservation of energy through the application of Newtonian force equilibrium allows for the determination of likely stress state variables. The equilibrium of saturated and unsaturated soil systems can be determined through superposition of what is known as coincident equilibrium stress fields. Equilibrium considerations must start with a legitimate free body diagram. Unfortunately, a wavy plane through the contact points between soil particles does not constitute an acceptable free body diagram for force equilibrium. Historically, this has been attempted, but an acceptable free body diagram must be multi-dimensional and have unbiased smooth sides, according to Fung in 1965. Let us consider several possible types of materials, starting with a one-phase solid such as concrete or steel. In undergraduate classes on strength of materials, our students are taught about a stress tensor that contains total stresses along the trace of the tensor and shear stresses for the remaining components. This is the starting point from which a science can be developed for a one-phase solid. The source of this stress tensor comes from the equilibrium consideration of the one-phase solid material. The tensor is known as the stress state at a point in the continuum. Consideration of conservation of mass leads to a deformation tensor, as shown in this slide. Along the trace of the tensor are normal strain variables, which can be added together to give the overall volumetric strain. There are also 6 shear strain components in the tensor. The lower part of the slide shows that conservation of mass and continuity must be satisfied when the material under consideration has additional phases, for example, the air phase and the water phase. A saturated soil is a two-phase system. Terzaghi in the 1930s noted that it was the difference between the total stress field and the pore water pressure field that gave rise to a variable of great value for describing the physical behavior of saturated soils. The resulting variable was called effective stress. This variable is often written in the form of an equation. However, a more accurate and complete picture of effective stress shows that the stresses are really the trace along a tensor. Since effective stress applies independently in 3 directions, there are 3 components. It is noteworthy that there is the effective stress component in the X, Y, and Z direction. And the equilibrium equations that can be written apply for the soil structure of a two-phase soil system. The components of the stress state for a saturated soil can be shown as the surface tractions from the equilibrium equations for the soil structure. When the stress components of the stress tensor are shown on a cube, they are designated as the stress state at a point for a saturated soil. This illustrates why effective stress is such an important starting point for the development of a science-based soil mechanics for saturated soils. Time does not permit the derivation of the equilibrium equations for an unsaturated soil as a multi-phase system. Such an analysis was published by Fredlund and Morgenstern in 1977. The analysis showed that 2 separate or independent stress tensors could be extracted from the equilibrium equations for the soil structure and then written in the Cartesian coordinate directions. The tensors shown on this slide are referred to as the net normal stress tensor and the matrix suction or soil suction tensor. Two independent stress tensors are required to define the stress state for an unsaturated soil. One of the reasons that two stress tensors are required lies in the fact that one tensor is always isotropic in nature, while the other one has anisotropic behavior or maintains shear. The two independent stress tensors can be placed on the sides of a cube to illustrate the designation of the stress state at a point within an unsaturated soil. This forms the general stress state description for an unsaturated soil. It should be noted that the designations are devoid of soil properties. It is important to note that there is a smooth transition between the stress state designation for an unsaturated soil and the stress state for a saturated soil, and vice versa. When a soil becomes saturated, the pore air pressure becomes equal to the pore water pressure, and the matrix suction term goes to zero. As a consequence, the matrix suction tensor disappears, and the stress state designation becomes that of a saturated soil. It can also be noted that there is a hierarchy amongst the stress components, with total stress always being the largest and pore water pressure being the smallest, with the possibility that the pore water pressure can even go into the negative or tensile state. When the water phase of a dry soil becomes discontinuous, the stress state of the dry soil can be written as the difference between the total stresses and the pore air pressure as shown in this slide. This is the designation of the stress state at a point for a dry soil. The above series of slides shows us that there is a smooth transition between saturated and completely dry soil states. The transition points are defined in terms of degree of saturation of the soil and the continuity of the fluid phases. The two most important points are the air entry value of the soil and the residual stress state. In the next lecture, I will show how the soil water characteristic curve, or the SWCC, can be used to relate stress states and the degree of saturation states. It is important to be able to visualize the linkage between the stress states associated with theoretical considerations and the stress states found in the field or in situ. Total stress conditions can be computed in a similar manner for both saturated and unsaturated soils. This is good news. The pore air pressure also will generally remain near atmospheric conditions for most geotechnical engineering problems. This is also good news. It is the pore water pressure, however, that can be highly negative for unsaturated soils and can be a challenge to measure both in the laboratory and the field. Under geostatic conditions in the field, the total vertical stresses can be calculated as the sum of the overlying total unit weights. The horizontal stresses can be written in terms of an earth pressure coefficient at rest, K sub naught. Unfortunately, there is no accurate theory to calculate the earth pressure coefficient at rest, although it can be estimated if the elastic properties of the soil are known. Matrix suction in the soil can significantly affect the lateral earth pressures at rest, opening the possibility for tension cracks to form. The tension cracks allow the earth pressure coefficient at rest, K sub naught, to go to zero. Under sloping ground conditions, total vertical stress states can be computed by switching on the gravity force through the use of the unit weight of the soil. The complete stress state is computed for every point in the continuum. All components of the total stress state can be plotted and contoured. This slide simply shows the contours of the vertical total stresses calculated. Under sloping ground conditions, the total horizontal stresses can only be calculated based on an understanding of the soil properties such as Young's modulus of elasticity and Poisson's ratio. The calculation of total stress fields is often made more difficult because sloping surfaces are usually the result of a series of soil excavations or the placement of fill. The stress state at any point within a soil mass can be plotted on a Mohr diagram. However, the Mohr diagram needs to be extended into a third dimension when unsaturated soils are involved. In other words, the matrix suction variable renders the Mohr diagram a three-dimensional plot. Mohr circles can be plotted in the usual manner at the appropriate suction level. It is also possible to write stress invariants for any unsaturated soil. Since there are two independent stress tensors, there can be twice as many stress invariants. In other words, first, second, and third stress invariants can be written for the first and second stress tensors. Only the first stress invariants for the first and second stress tensors are shown on this slide. The following point can be made. Any stress description written for a saturated soil can also be written for an unsaturated soil. The state variable of greatest interest in unsaturated soil mechanics are those related to the soil water characteristic curve, that is, soil suction and water content. The emphasis today will be on the measurement of soil suction. It is easier to measure soil suction in the laboratory than in the field, although both can be a challenge. Matrix suction is difficult to measure directly because of the problems of cavitation in the fluid that is part of the measuring system. Total suction is also difficult to measure because of the need for accurate temperature control. The theoretical concept of soil suction was developed in the early 1900s. The concept has been applied mainly in the study of soil, water, plant systems. The unifying theory involves a thermodynamic relationship between soil suction and the partial pressure at the air-water interface. Total suction can be related to the relative humidity of the soil through application of the universal gas law as shown in this slide. There appears to be only two main variables that affect the partial pressure in the air adjacent to a water surface. These are the tensile stress in the water phase and the amount of salts in the pore water. The thermodynamic equation presented on the previous slide can be plotted to illustrate the relationship between relative humidity and soil suction. The total suction scale on the abscissa is plotted from 100 kilopascals to 1 million kilopascals. It should be noted that the relative humidity of the soil does not decrease significantly until almost 10,000 kilopascals of suction. The matrix suction range of greatest interest in geotechnical engineering usually ranges from about 1 kilopascal to 1,500 kilopascals. Matrix suctions below 1,500 are referred to as being in the low suction range. Relative humidity changes are extremely small in this range. There are two components that combine to form total suction. These are, first, matrix suction, defined as the difference between the pore air and pore water pressures, and secondly, the osmotic suction component. The matrix suction is of greatest interest in geotechnical engineering in the suction range below 1500, and the total suction is of greatest interest in the high suction range when the suctions are greater than 1500 kilopascals. In lecture number 3, I will discuss the use of the soil water characteristic curve and explain that the suction axis generally has matrix suction plotted in the range up to 1500, and then has total suction plotted on the same axis for suctions greater than 1500 kilopascals. The components of suction as well as total suction have been independently measured for several soils. Typical results are shown on this graph. Total suctions were measured using psychrometers, while matrix suctions were measured using the axis translation method. Osmotic suctions were measured by squeezing the pore fluid and measuring its electrical conductivity. The solid line represents the sum of the independently measured matrix suction and the osmotic suction values. The results indicate that the measured values of the individual components of suction are quite consistent with the measurement of total suction. The potential range over which soil suction can vary is quite large. It is not surprising that a variety of methods and techniques have emerged for the measurement of soil suction. This table gives a partial list of some of the technologies that have been used, along with a designation of the component of suction being measured. The range over which each suction can be measured is also shown. Let us briefly comment on some of the measurement devices. The conventional tensiometer has been extensively used in agriculture for field measurement of matrix suction. The ceramic tip has an air entry value in excess of 100 kilopascals. It has a suction measurement range from about 1 kilopascal to 90 kilopascals. The tensiometer can be connected to a data acquisition system for selected time interval readings. Each tensiometer should be serviced prior to installation to ensure that it can sustain a tensile stress in the water phase of at least 90 kilopascals. Servicing may also be required on an almost daily basis if the suctions are to be maintained near the capacity of the tensiometer. The quick draw tensiometer operates on the same principles as the conventional tensiometer. It is intended for making spot checks of matrix suction at locations near the ground surface or along the side walls of an excavation. Between measurements, the ceramic tip can be kept in a water-saturated cotton battened reservoir. The tensiometer kit also contains a coring tool and a cleaning rod. The quick draw tensiometer should be serviced to ensure that it can sustain a tension of at least 90 kilopascals prior to taking it into the field for suction measurements. A company called UMS recently developed a mini T5 tensiometer. The ceramic tip is 5 millimeters in diameter and has an air entry value of about 200 kilopascals. The manufacturers suggest that it can measure matrix suctions up to about 200 kilopascals over a limited time period. If cavitation occurs, The tensiometer can be serviced and restored to its original capacity. The tensiometer comes with a special fluid that is used for servicing the tensiometer. A number of so-called high suction tensiometers have been developed in the UK, Canada, and other countries. The manufacturers of these tensiometers make claims of being able to measure matrix suctions up to and exceeding 1,000 kilopascals. It is difficult for the tensiometers to sustain high suctions over a long period of time. The water in the compartment below the 15-bar ceramic disc is initially serviced through the use of a cycling high pre-pressurization of the water. These tensiometers work quite well in the laboratory, but need to be reserviced following a cavitation. Researchers at Nanyang Technological University in Singapore developed a high suction tensiometer that could be mounted along the sides of a triaxial specimen. This negated the need to use the axis translation technique when testing the soils with matrix suction values greater than 100 kilopascals. It was found that matrix suctions greater than 200 kilopascals could be sustained for at least 1 week while the soil specimen was being tested in shear. Laboratory pressure plate apparatuses can be used to measure matrix suctions well in excess of 100 kilopascals. The maximum suctions that can be measured mainly depend on the air entry value of the ceramic disc in the pressure plate apparatus. The axis translation technique allows the air pressure, or the atmospheric pressure, to be elevated. In this way, the water in the measuring compartment can remain positive, preventing cavitation. A pressure transducer mounted in the base of the pressure plate apparatus allows the ambient air pressure to be elevated until the water pressure remains near zero or even positive. The following slide shows some typical matrix suction measurements using the axis translation device. This slide shows the results of axis translation measurements on 4 samples of highly plastic Regina clay. The suction measurements ranged from 40 kilopascals to 410 kilopascals. Each measurement took from 1 hour to 8 hours for the matrix suctions to be measured. Attempts to circumvent problems related to water cavitation have led to the development of other devices such as the thermal conductivity suction sensors. In this case, a heat pulse is generated near the center of a specially designed ceramic stone. Thermal conductivity measurements are calibrated against an applied suction, matrix suction. The ceramic stone is about 2.5 centimeters in diameter and has a low air entry value, typically less than 10 kPa. The temperature rise in the ceramic stone is a function of the degree of saturation of the ceramic stone. The sensor measurement is referred to as an indirect measurement of matrix suction. A typical measurement of the matrix suction using this device is shown on the following slide. In this case, a thermal conductivity suction sensor was placed in each end of an undisturbed Shelby tube sample of Regina clay. One of the sensors was initially dry, while the other sensor was initially saturated with water. This means that one of the thermal conductivity sensors needed to take on water as it came to equilibrium with the water in the surrounding soil. The other sensor needed to give up water as it came to equilibrium with the water in the surrounding soil. After a couple of hours, both sensors registered a matrix suction value of approximately 170 kilopascals. Let me conclude this lecture with a few comments about the measurement of total suction and osmotic suction. It is important to remind ourselves that most practical engineering problems can be analyzed using matrix suction as the stress state variable. Total suction is mainly of interest with respect to analyzing problems related to actual evaporation from the soil surface. High total suction measurements all culminate in a total suction of 1 million kilopascals for all soils. Total suction is related to the vapor pressure or relative humidity in the soil. Mention is made of some of the total suction measuring systems that are available. These are, first, two types of psychrometers. Second, the chilled mirror potentiometer. And third, the filter paper technique. These methods rely on either direct or indirect measurement of the relative humidity. The main components of a Peltier psychrometer is the thermocouple, which is comprised of two differing materials. Passing a current through the thermocouple results in a small drop of water being condensed on the thermocouple tip. The rate of evaporation is a measure of the relative humidity in the soil, which in turn is related to total suction through the gas law. A constant temperature environment is required for accurate measurements. Filter paper has relatively a constant relationship between vapor pressure and its water content. The calibration curve for one brand of filter paper is shown on this slide. If the disc of filter paper is placed above a soil sample within a sealed container, the filter paper will come to equilibrium with a total suction in the soil sample. This process may require up to a week for complete equalization to occur. The chilled mirror water potentiometer measures the dew point on a small soil sample. The dew point allows a direct measurement of the total suction of the soil. If the small soil sample and the measurement device are at the same temperature, measurements of total suction can be made within minutes. The short time required for the measurement of total suction has made this device a popular laboratory device for measurement of total suction. The device appears to give reproducible and accurate results in the range of total suctions from 1,000 kilopascals to near 1 million kilopascals. Osmotic suction is a function of the amount of salt in the free pore water. A high pressure squeezing device can be used to squeeze a few drops of water from the soil specimen. The electrical conductivity of the pore water can be measured using an electrical conductivity meter. There is a direct relationship between electrical conductivity and osmotic suction, as shown by the equation on the slide. Fortunately, this relationship does not have a significant dependency on the type of salts that are in the pore fluid. This lecture has focused mainly on the measurement of the matrix suction stress state variable, since it is of greatest significance for the implementation of unsaturated soil mechanics into geotechnical engineering. There are other state variables such as water content that are also important. However, time does not permit coverage of all possible stress state variable measurements. The next lecture will describe the meaning and the importance of the soil water characteristic curve, commonly referred to as the soil water characteristic curve. Thank you.